conference every year until the end of time. So all in favor? All opposed? Okay, would someone tell Ron about that when he comes in? Okay, thank you. All right, so this is, I hope you will find this to be an enjoyable talk. It's a departure from some other applications of ferroelectrics that my group has been involved with. I think it's really a very interesting idea, and so I'm going to be telling you about some ultra-fast electric field control of giant temperature change in ferroelectrics. This idea came out from some experimental observations of our friend and collaborator Aaron Lindenberg and an extremely talented graduate student, Yubo Chi, and a former student, Shi Lu. Now, Yubo has also graduated and is a postdoc with Karen Rabe at Rutgers, and Shi Lu is right here as part of your home team. Basically, we all know that there are Landau-Ginzburg relationships that relate temperature and polarization, and we're accustomed to changing the temperature of a ferroelectric and seeing it go through a phase transition, but this relationship can be inverted. The cartoon here is that you have a material with a certain polarization, you apply an electric field, maybe even a transient electric field, and you change the temperature and you change the phase. So we're going to talk about that in some more detail as the presentation progresses. Okay, so the electrocaloric effect is the word for this phenomenon where as you change the structural phase of a material through orienting or disorienting dipoles, you can change the temperature. And so, as I said, we may be more familiar with the pyroelectric effect because all ferroelectrics are surely also pyroelectric, and there are many other interesting pyroelectric materials out there whose polarization change with temperature. But the idea is that if an atom's getting its bond valence by summing up the bonds of its neighbors, maybe it likes that all those bonds have a vector sum of 0, or maybe it likes that it has some asymmetry to its local environment, and that can be input with this term. And then finally, we had a small angle potential that if some of the octahedra in the model without this term have too large or too small octahedral rotations, there's a fine-tuning that can be done with a single parameter here of how much the octahedra like to rotate. Okay, so this is a little bit more in depth about these potentials. So as I was mentioning, this is the way we calculate the bond valence. It's the sum of the individual bond valences, and that is an inverse power law of the distance between each atom and its nearest neighbors. And then we get the energy of the bond valence as its deviation from its prototypical valence. Okay. And then this bond valence vector, you can see an example here that if we calculated bond valence for water, it might have two perfectly good OH bonds and be happy, and here it might have two perfectly good OH bonds and be happy, but it wouldn't know that water actually wants to have a bend structure unless you reward having the sum of the two vectors be non-zero, and so you make a minimum around some value that would allow water to know that it should have a polar and low symmetry shape. And so that's been quite successful for us. Several students have contributed strongly to the methodology of bond valence, including both Yubo and Shi. So you will see some of the methodology work implemented here. Okay, so one of our recent successes is getting this bond valence model to work for barium titanate. It's a prototypical ferroelectric material, but it has all the phase transitions from rhombohedral to orthorhombic to tetragonal to cubic, and so it was fairly difficult to do. And so there was some simulated annealing in which you take parameters and do molecular dynamic simulations and then check with density functional theory whether the energies and the forces agree well, and if they don't, then you can use additional structures to refit until you're happy with the parameters. And these are just the parameters that I mentioned to you, the prototypical bond lengths between the cations and oxygen, the charges, the short-term repulsion parameters, and so forth. Okay, and so as you can see here, the model is able to reproduce all the phase transitions, showing that you have equal polarization along X, Y, and Z at low temperature, and one of the components drops to 0, and a second one drops to 0, and then the last one drops to 0. So this would be the Curie temperature. So the temperature is all too small compared to experiment, but many of the local structures appear to be quite accurate. And it actually, the point is it's designed to reproduce first principles calculations. It's not fit to experiment. And if you do molecular dynamics with density functional theory, you would also get similar suppression of Curie temperatures. Okay, so now we can show you computational experiments relating to the electrocaloric effect. And so each of the slides is a little different, so I'll tell you about it in some detail here. So the first thing to look at is we have done an equilibrium run where we let the atoms respond at some temperature for some amount of time, and they're just all thermally moving the way they might wish. So then here is the electric field in kilovolts per centimeter, and you see for some time it's zero. There's actually quite a lot of equilibration before zero, but at some time we start to increase the electric field. Can you see? Going up linearly, there's a linear ramp, and then we leave it at some finite value. Okay. And the potential energy actually goes up. So this is what I was saying to you. This is a negative electrocaloric effect. You may have expected that as you apply an electric field, you orient the dipoles, making the potential energy go down. But in this case, the electric field is applied along the 110 direction. You see up here? And if you start in the rhombohedral phase, this will favor polarization along X and Y, and that will send a signal to the material to scramble its Z polarization. And that's what happens. So you watch the polarization as a function of time. X, Y, and Z are all finite, but then upon experiencing this electric field along the orthorhombic direction, it becomes orthorhombic. And so that is a consequence. The biggest consequence is losing this Z component of polarization. The X and Y go up a little bit along the electric field direction. So you can think of it this way. As a function of temperature, the rhombohedral potential energy is lower than the orthorhombic, but as you apply electric field, you're driving the system to higher potential energy and lower temperature, and it's crossing over to the orthorhombic state. And so you see a change in temperature of about -1 Kelvin as a result. Okay. So now this is going to examine negative electrocaloric effect in the transition from tetragonal to cubic. And so here, the electric field is applied along the y-axis, where the polarization is along the z-axis. So the electric field is perpendicular to the polarization. Okay, so now here is the electric field trace. It's different from last time. So we have our equilibration run where the electric field is zero, and then we have the electric field go negative, and then positive, and then back to zero. And this serves to scramble the electric dipoles quite effectively, that they don't have time to, in an adiabatic way, rotate and follow the electric field, because by the time they do, the electric field is the other way, and it has the consequence of just convincing the individual dipoles to scramble. And so if we make a graph of the volume average polarization along the X, Y, and Z directions, here it's tetragonal with polarization along Z, it starts to rotate into the Y direction, but pretty quickly it all scrambles, and it goes to the cubic local minimum in free energy, as opposed to finding one of the tetragonal variants. And so this leads to a change in temperature of more than 2 Kelvin. Okay, and then finally, if you look at lead titanate, we know lead titanate has a much higher TC and a much larger latent heat. And so all these phenomena apply rather similarly, but the energy scale is just significantly larger. So here we exhibit a different case. This is just for exercising the ideas. Here we apply an electric field that's anti-parallel, but it's timed to be short enough that it doesn't allow the polarization to follow. So the electric field is zero, and then we have an anti-parallel electric field for a short time, and then it turns off again. So a half-cycle pulse. And the temperature is constant, and then it drops significantly right around the time that the electric field is being applied, and the polarization goes to zero. So we have driven the system from the tetragonal phase to the cubic phase, and it's significantly lower temperature. And it's supercooled in the sense that at this temperature, it really would prefer to be in the tetragonal phase, but it doesn't know that. It takes time for nucleation and growth to reassert itself. Okay, and so here is a short but nice movie of this. So this is the case of tetragonal barium titanate. Do you see the dipoles are pointing up, but the electric field is applied along the horizontal direction. Okay, so they're undergoing thermal motion, but then some of them are starting to rotate. You can see that there's just a greater disorder in the dipoles, but some of them are visiting, being 90 degrees away from the original direction. And as this happens, the temperature is dropping the whole time because the potential energy is rising. They're not aligned. They're not nearly as aligned as they started. And so this is ultra-fast negative temperature change induced by electric field. Okay, good. Huh. Okay, there we go. Okay, so the basic idea is if you have a Landau-Devonshire model of the energy versus polarization, for very low temperatures, it's a double well. We're very familiar with this. You have maybe up polarization and down polarization. But if you get near the crossover between the polar state and the nonpolar state can be a local minimum. It's not favored, but it can be a local minimum. And then eventually you get to a high enough temperature that the minimum at zero polarization is the absolute minimum. And then you're in the paraelectric state. But there's this crossover region where you have accessible to you states with significantly different potential energy. And that opens this opportunity for using the latent heat. And so schematically, what we're doing with this electric field is we're driving the polarization away from its favored value, and for certain pulse shapes and durations, it can become convinced that the closest minimum is the p equals 0, 1. It'll fall into that minimum and stay there for some amount of time. And depending on how close we are to the temperature at which the zero polarization minimum goes away, or becomes dominant over the positive polarization, that sets the time scale over which this can be metastable. And in order to have such a Gibbs free energy profile, we have temperature near the Curie temperature. Not below, but not quite, not too far away. And the electric field profile should be properly designed. Okay, so what have I presented to you today? We talk about the electrocaloric effect always from an energy point of view. As I say, my friends often talk about entropy redistribution, and I think that everything I told you about today can be worked out in that language. But it turns out that you can lose track of some energy when the system is not maintained at quasi-equilibrium. And so we think this energy point of view allows you to really understand what you're doing better and more simply. And to get large temperature changes, you need strong ferroelectric systems with a large latent heat. And the electric field profile can either be perpendicular to the polarization, anti-parallel, or in the third case that I showed you, you can apply the electric field in a way that encourages some components of the polarization, but not others, selectively removing one component of polarization. All of these are possible. And the largest energy change we see is that for lead titanate. And so this is a summary of some of the results. There's a range of temperature changes that I showed you today. And so it's a pleasure to remind you that this was a very fruitful collaboration with Aaron Lindenberg, who is at SLAC and also at Stanford, and Shi Lu from the Carnegie Institution for Science, and Yubo Chi, who is no longer at the University of Pennsylvania, I'm sorry to say, but I'm happy to say he's now productively working at Rutgers. And so with that, I thank you for your attention, and I will be happy to take your questions.
Okay, great. So we have time for a few questions.
Andrew, I understand that the last process you discussed depends on how fast you switch on the electric field, or what is the profile in time. Does it mean that you actually transfer some momentum?
I guess you transfer a little momentum. Sure. Not a lot. Yeah. But in fact, what we're really doing is telling them to scramble. You see, they're not following the direction of the electric field. Under the influence of the electric field, the state they were in is destabilized, but then they thermally go to other states.
So, yeah. Oh.
I mean, beautiful talk, by the way. Did I understand correctly that the first case is more of a quasi-static, equilibrium case where you tickle it from the rhombohedral phase to the orthorhombic phase by applying a field kind of in equilibrium, whereas the second and third one both require this trick of kicking it into the undercooled higher free energy state. Because it seems to me that only the first one is really useful for refrigeration purposes. Maybe I don't understand.
Oh, I think that's okay. The first part you're right. I think the second part I'd like to, at least in a kind way, quarrel with. So yes, I think that when we converted the 111 to the 110, we think that's a great thing that can be done and leave the electric field on as long as you might wish. Yes. Anytime you're trying to access the paraelectric state, I think we agree that you can get the temperature to go negative, but then you're wondering what will happen later for the rest of the cycle. And I feel like we could couple a negative electrocaloric effect with a positive electrocaloric effect. We could apply an electric field that does the conventional thing of aligning dipoles and making the temperature go up. We could do negative ECE and positive ECE, and that should be just fine.
Thanks for the nice talk. So normally when you do this in molecular dynamics, this direct estimation of the caloric effect, so you should, in principle, you have to be quite slow in switching on and switching off the electric field. So for instance, if you had here a relaxor, so it has been shown that if you just do like an abrupt change of the electric field like this, you are not getting the right due to ergodicity, you are not getting the right estimation. So how that really affects? So have you checked that in your work? So if that pulls, really you change. So rather than doing it ultra fast, you do it a bit slowly. So that the final result changes.
That's a really well phrased and erudite question. I think what saves us is we are driving the system to a higher entropy state. So even if it's in an interesting local minimum, we're raising it up out of that, and then it is ergodic at the end, you see? And so I have no concern that if we do it slower, we will get something different. But we did try a range of times. But if you say, what if you try it over a millisecond instead of a nanosecond, I think it may have enough time to nucleate and reform domains. There's only so long that these states will remain supercooled. So we're trying to beat that. So to some extent, fast is the point, and non-ergodic is the point in a way. But when we access the paraelectric structure, I think we're avoiding some of the concerns that you raised.
Thank you, Andrew. Unfortunately, we're going to have to stop there with questions to stay on time so we can have dinner at a reasonable hour. So Andrew will be around so we can take more questions. Let's thank him once again.
Okay, thank you. Good luck. That one.
Perfect.
Okay, so our next speaker is Brahim Dikal, who will speak about ferroelectric features at the service of solid-state coolers. Thank you.
Thank you very much for this one. Okay, I'll try not moving. Okay. Okay, thank you very much. Good afternoon, everyone. So I will continue this topic about electrocalorics. So the title is actually, the idea of this title is just to show you what we may do with ferroelectrics to play with the caloric response of these systems. So we had a nice introduction by Andrew just before, but let me just show you the real people who worked in this topic for this presentation, and especially the PhD, which are some of them are now postdocs. So Yang Liu, Bobo Tian, Chuang Yuan Li, Lee Phillips, Junin Li, and Romain Fay, who all these guys really worked hard to get all the results I'm going to show you. So I don't need to introduce the context. Indeed, we need to find new solutions for refrigerations and air conditioning because of this harmful refrigerant, which is HFC's gases. And what we can do to save and to make our planet great again is to find new solutions. And one of the solutions is electrocalorics, of course. I guess you recognize the alien here. He has a red cap. And to show you this slide, this very interesting slide made by our colleague from Germany. And this is the, let's say, efficiency as a function of decreasing level of maturity for different technologies. Of course, this one is the most used one. And we see that today we reach something like 60% of the efficiency, while we could reach 75%. But if now we have a look to the electrocalorics, which is a less mature technology, but we see that we may expect much highest efficiency. And nowadays we are around, let's say, 10–15% of efficiency. The big advantage of electrocaloric is solid state system, and we have to apply an electric field, which is sometimes much easier than, for instance, magnetocalorics, where you have to apply a magnetic field, which is usually very strong, of the order of a few Teslas. So this slide has been more or less described by Andrew just before. So the idea actually is to play with the order and disorder. The idea of applying an electric field is to order the dipoles in your system, and once you order these dipoles, if you are working in adiabatic conditions, then you have heating of your system. If you keep this field applied, then you can remove the heat, keeping the dipole, of course, aligned, and then you switch off the electric field, always in adiabatic conditions, and then you have decreasing of the temperature. And this can be applied for magnetocaloric, elastocaloric systems. So how we measure this? Actually, most of the time, people use these so-called Maxwell relationship, and the idea is just to measure the polarization as a function of temperature, and then you take the derivative of the polarization with respect to the temperature, and then you calculate the change of temperature. It works rather well, actually, but keep in mind that the value that you will have, it's an estimation. So it's better to use this technique for trends, essentially. And there are also some direct techniques, and some of them are described here. For instance, you can use calorimeters. Then you apply electric field. You have a heat flow here. You switch off the field. You have an endothermic heat flow. You can also use infrared camera, which is very nice because you can have then a view of the heat extracted from your system. So this measurement, for instance, have been done by Romain Fay. He just took MLC capacitor here. You have them on your laptops. And applied the electric field, and with time we see that there is a heating of this MLC device. So once again, you start at a given temperature, you apply the electric field, then you have enhancement of, increasing of the temperature. The heat is released to the environment, then you go back to the initial temperature, you switch off, and then you have a decrease of the temperature. And of course, you may cycle this many, many, many times. So I'm coming to the menu, actually. So the idea, actually, once again, is to show you some features that you may exploit or explore in order to improve the caloric properties, and some of them are listed here. So play with the composition, with conventional inverse or negative, as has been described just before by Andrew. We can also play with defect engineering or even with multi-calorics things. So from composition point of view, the idea is basically to bring typically the paraelectric to ferroelectric phase transition to room temperature, for instance, like in this solute solution, but at the same time, try to have a maximum of disorder in your system. So if you have a lot of coexistence or proximity of other phases, it means that you can easily find different direction of polarization, so you increase the disorder of your system. It's not only related to paraelectric to ferroelectric phase transition. You can also have in ferroelectric to ferroelectric phase transition, it works also. So don't fix only paraelectric to ferroelectric phase transition. So you can find also, for instance, in this KNN-based system, close to the MPB, we can also find interesting change of the temperature. What we can do, this is the negative part. Actually, when I say negative electrocaloric, the people from magnetism, they don't like it. Negative means negative, you know, it's not good. And then they used to say inverse, okay? In the sense that once you apply the electric field, inside of having enhancement of the temperature, you have a decrease of the temperature. So it's not negative, it's rather good, as Andrew stressed it, yeah? So what we did here, we took an anti-ferroelectric system, very nice double hysteresis loop, and we applied the electric field, of course, to measure this polarization. And if we now plot the polarization as a function of temperature for different electric field, let's start by the high electric field. You see that the polarization is decreasing while the temperature is increasing. Of course, if you inject the derivative here, you will have delta T positive. However, when the electric field is lower, you start by having an increase of the polarization first. If you have the increase of the polarization, this derivative now is positive, and then as we have a minus here, delta T becomes negative. And indeed, in case of this antiferroelectric, we have a negative or inverse electrocaloric effect and a positive or conventional electrocaloric effect. And to explain this, basically, the idea is the following. You take a kind of antiferroelectric state, so dipole up, dipole down, and then you apply an electric field along that direction, for instance. What will happen at the beginning? This one wants to turn to follow the electric field. But of course, at the beginning, it was ordered. And then it starts to disorder before reordering. You see? If you start with a system which is ordered, and then you go toward disorder, then you have delta T negative. Okay? And actually, you can exactly apply the same kind of story. It works very well for antiferromagnetic. And as has been described by Andrew just before, of course, if you have the polarization that way and you apply an electric field in that direction, you will force the disorder to increase in your system. This is what has been described just before, which is very nice. From modeling point of view, this is for kids, you know. What we can have also, we can have some asymmetry effect. For instance, in case of this system, we measure, you see, we apply the electric field here, then we have delta T increasing. This is a conventional electrocaloric effect. But when you switch off, we have delta T negative, but the amplitude is not the same. In a normal system, the amplitude for positive and negative, it's exactly the same. Here, the main reason of that is because we are playing with a non-ergodic system. And depending how you go toward this ferroelectric phase, you will not have exactly the same thing. So this is something that we can also use, having to have a delta T positive bigger than a delta T negative. And we can think to a way to design a device with this mechanism. What we can also do is to play with a disorder. And this has been nicely presented yesterday, I guess. It was a long day already, by Tadei, when he showed how he can play with the doping play on the domain walls. And actually, defects in ferroelectrics have been used in many, many applications for hardening ferroelectric polarization, etc., etc. And here we can do exactly the same things. So in this case, for instance, we took this composition, and then we add some copper inside. The copper coupled with the oxygen vacancies to make a permanent dipole, a defect dipole. And because of this, you see, we start with the non-doped system, which is normal ferroelectric. And once you dope, we have this pinched hysteresis loop, as Tadei showed yesterday. And if you apply a given polling condition, you can even strongly change the hysteresis loop. This is very interesting because you can now think in that way. What we need disorder. And of course, the way of having disorder is to have a P max much bigger than P remanent. It means that you have a lot of entropy in your system. Okay? So in this kind of system is very interesting, and that one also at the same time. And what you can see also that by playing with the disorder, for instance, you can also enhance the energy storage, which corresponds to the area, which is exactly here. So you see, in that case, the area is much bigger. So defect is very, very interesting way to design some peculiar properties. So let me show just some results with this defect engineering. First, once you add the copper, you can apply much higher electric field. And higher the electric field is, higher delta T is. Okay, so this is already, you want something already. And what we did also here, we cycled many, many times, because we know by cycling we can move also the defect. We have to take into account the mobility of this defect. And you see that when we start at the beginning, it's like this. Once, after 10,000 cycles, it changed a little bit in the sense that it starts to have the polarization. It looks like more ferroelectric than pitched one. But if we remove the electric field and leave it during 24 hours, we recover exactly the same state as beginning. So you can think also to design a kind of device by playing with these pitched hysteresis loops, and of course cycling and aging in the system. We did also the same kind of things. I will not go into the details here, but we played also with this hysteresis loop to see how the delta T evolved as a function of the number of cycles. And there is a very nice stability of this delta T, meaning that we, I guess, are ready to use this kind of devices, even if delta T in that case is not so big. But once again, it's bulk system. If you want to increase the delta T, you have to apply a higher electric field, and the way to have an highest electric field is to make thinner systems. The MLCCs, for instance, multi-layer capacitors, are very nice for this kind of applications. And actually, Murata is working a lot now in this direction. Murata company. So what we can also do with ferroelectric have also elastic transition. We know that once the polarization appears in the system, there is a distortion of the system. Therefore, what we can do, we can not only apply electric field, but we can apply a stress on your system. And if we combine both, we can enhance the global delta T of our system. So it's a way also to play, a so-called multicaloric aspect, which I guess might be very, very interesting also to exploit or to explore in the next years. Something that we did in the multicaloric, for instance, is to take this iron rhodium system. It's a magnetic system. It's very nice magnetocaloric system. The problem of this guy, first, it's expensive, as I used to say, but also this first order phase transition. This is the magnetization as a function of the magnetic field, and you see that we have a huge first order phase transition, and if you want to cycle, you have a lot of losses in that case. So you have to find a solution. One of the solutions that we propose is the following one. We take iron rhodium, we put it on barium titanate, this ferroelectric. And now why we consider this system? Because we know that the magnetization of iron rhodium can be controlled by the voltage that we apply on barium titanate. So by playing with magnetic field and electric field, we could play on the magnetic arrangement of iron rhodium, and this is what we did actually. So we start with this one, and inside, we applied here magnetic field, and we come back, removing the magnetic field. But now the problem of this, as I told you, the only energy that you will extract from your system is only this triangle here. Here what we did, we applied the magnetic field. This is the black curve here. And we remove the magnetic field, but at the same time, we apply a voltage on barium titanate. And in that way, we are able to follow more or less or very close to this black curve. And now the energy that we have is exactly that one. So we succeed to remove the hysteresis loop of the magnetic property. Actually, these magnetic losses are not fully lost, of course, because at the interface we have also elasticity which appear. And what we did actually, we just transform a part of the magnetic losses into elastic losses in that case. But in the end, if we make some calculation, we can see that we have a better efficiency once we use these two works, these two, electric field and magnetic field, rather than only magnetic field. So this is my conclusion. So the idea is indeed to show you that we can think about ferroelectric for solid-state refrigerant. I showed you some of the strategies that we are working on, but like composition, conventional, inverse, asymmetry, defect engineering, ergodicity and non-ergodicity, applying mechanical stress. We can combine different stimuli, but not only, we can also consider different systems like relaxers. There are already some very nice work done using a relaxer. We can consider composite or even other completely exotic materials. We have also to take into account the effect of the interfaces, the effect of ferroelectric or ferroelastic domains, domain walls, etc., etc., etc. So many work to do. From a material point of view, from the understanding of the physics, from modeling, we had just before a very nice talk showing that, and in the next talk we will have also very interesting modeling aspect. And not only from this understanding, I would say, we have also to make some improvement into the integration and the device aspect of these of ferroelectric for electrocaloric properties. Thank you very much.
Okay, great, thank you. So we have time for one or two questions. Any questions from the audience?
Him for the very nice talk. You showed this delta T in these doped samples, which was bigger than in undoped, right? This is how I understood. So the delta T that you measured on doped samples was higher than on undoped, right?
Yes.
So the origin is this pinching of the loops. So you think you get bigger differences between the max and
yes.
Polarization zero field. Is this the origin of that?
Yeah, this is what we're thinking. Actually, what we did in that case, we also measured directly the thing. And it corresponds rather well with the value that we measured here. And we do think, indeed, that it's because of this pinched curve. You see, once again, you have P max. Let's say you start without an electric field, it's zero, on average, of course. But once you apply the electric field, you can change the polarization a lot, compared to the ferroelectric one. And this is the reason. Yes.
Is this pinching changing by cycling?
No, yes. Look, yes, it's changing.
It means
that you will lose exactly here. You see? You see, we have an increase of the remnant polarization in the system. But in the end, if we follow, let's say, the delta T here, let's take for this one, it's for 10 Kelvin per centimeter, this one, you see that we have not a big change, I would say, of the delta T by itself.
I think it's nice that you have also slim polarization loop, so losses, hysteresis losses will be relatively low.
Yes, it's true. It's true.
And last question.
Okay. I guess I'll just limit myself to a couple of points. Do you think with the alliovalent doping that when you apply the electric field, vacancies will start to move? And in the magnetic ferroelectric composite, do you think we need to include the work done on the barium titanate in your overall energy balance?
So for the last one, yes, we have to include many things, actually. We have to, because once again, we have a thin film, and what we did, actually, we considered just the caloric effect of the magnetic layer. Of course, the substrate is much bigger, and therefore it will impact the caloric property, and the interface also, because you have elasticity at that place. So you have to consider magnetocaloric, elastocaloric, and electrocaloric, plus the losses of all of them, of course. And the first one was, I forgot. For the defect?
Moving
yes.
In this kind of case.
Yes, exactly. This is what yes, exactly.
Okay, let's thank the speaker once again. Okay, so our next speaker is from the University of Arkansas, and he'll be speaking about, is Xuzhun Jing, and he'll be speaking about barium zirconium titanate and lead magnesium niobate relaxer ferroelectrics, the electrochoric effects from atomistic simulations.
Good afternoon, everybody. My name is Zhijun Jiang from Xi'an Jiaotong University. Today, my title is about electrocaloric effect in barium, zirconium, titanate, and PMN relaxer ferroelectrics from atomistic simulation. First, I will introduce my co-authors, Dr. Lenhans Prokohorenko, Dr. Prosandi, Dr. Wang, Dr. Hogi, Dr. Idefi, and Professor Bleich. The second is I will thank the support of the DERPA, NSCF, China Scholarship Council, and AHPCC. My talk my outline is about first is introducing, second is methods, three is results, the last one is conclusion. First, I will introduce the caloric in application. The first paragraph is the electrocaloric material change in phase change when we apply electric field, induce phase change. Second is the thermal change when apply a magnetic field to get the thermal change. The third is the experimental measures infrared imaging to get the caloric effect. This circle is about the diagram of the caloric refrigeration cycle. The field we can apply the electric field, magnetic field, or another string, or so on. Next is what practical application can caloric effect be used in? Last talk about Professors Rapi and Dr. Hill also say it's about the solid color system which used in solid material and can reduce the impact. Can reduce the impact of the environmental. Can be reduced the green's impact. The second is about the electrocaloric effect. Last two talks is also induced more about this electrocaloric effect. So I just briefly see this electrocaloric effect is the change in temperature when induced by a change of electric field. This picture is the same as Dr. Steckhill just talk about the dipole from when there is no electric field. The dipole is disordered. When applied electric field, the dipole from disorder to orders induce the entropy decrease, then the temperature increase. So I don't say more about this one because Dr. Steckhill is also say more about this one. The second is the potential designs of the dual electrocaloric refrigerators and schematic of the components. This is the potential they use to design the electrocaloric refrigerators. Some more data, please see the reference. In order to understand the EC effect in relaxers, we have need to solve a lot of questions. The first one is can direct and indirect method provide different results below a specific temperature? The second is how does EC coefficient behave with the DC electric field for different temperature range? The third is can EC coefficient exhibit maximum for some intermediate field and different temperature range? The last one is how to understand the EC effect from its microscopy. So we choose two relaxers. The first one is BZT, second one is the prototypical PMN relaxer photoelectrics. First, I will introduce our method. Our method is based on effective Hamiltonians. This is our total energy. The first one is mu I is represent local mode under each site. The second is inhomogeneous string. The third is homogeneous string. This is a solid solution configurations. So we introduce the first method is indirect method. This indirect method is based on the Monte Carlo simulations. Also, it's based on the Maxwell thermodynamics relations. From this one, we can get the delta T change and the alpha. The alpha represent the electrocaloric coefficient. Here, we call this method is MC1. The second method is also the MC simulation. We call it based on the cumulant method. More detail, please see the reference. So the indirect method have two. The first is MC1. The second is MC2. MC1, MC2, both based on the Maxwell thermodynamics relationship. The second is the molecular dynamics simulations direct method. Here, we first choose the initial temperature, then rampings increase the electric field to epsilon to EF. Then we can get the delta T change. Then we can calculate the alpha. Alpha is the EC coefficient, can be obtained by taking the derivative of the delta T with respect to the different value of EF. So this method we call MD. This is a direct method. Our Hamiltonian in BZT predict series specific temperature. The first one is Tm is about 130 Kelvin. The second is the critical temperature. T star is about 240 Kelvin. The third one is T Bourne's temperature is about 450 Kelvin. This temperature is a good agreement with the experiment. So we use the MC1 method, the indirect method, to calculate the polarization and the function of the temperature. Then we can, according to the delta T formula, we can get the delta T as a function of delta E. The important thing is we got the EC coefficient as a function of electric field for different temperature. Here we choose four different temperature. One is 100, 200, 300, and 500. Why we choose the four different temperature? Because 100 Kelvin is below Tm, and 200 is between Tm and T star. The 300 Kelvin is between T star and T Boyce. 500 is about Boyce temperature. So, from the picture, we can see that above the Tm, the three methods can get nearly identical results, but below Tm, the indirect and direct method can't get the same results. Because below Tm, the system is non-ergodic. We can't use the normal Maxwell thermodynamic method to calculate the Rayleigh's EC effect. So we don't, here we don't trust the indirect method, we just trust the direct method. Though, to understand the EC response and the function of electric field, we, based on the Landau mode and derivative, the alpha is proportional to the derivative p squared with respect to the electric field. In other words, the alpha is proportional to this formula. To verify this model, we calculate the polarization square of the polarization as a function of electric field, then take the derivative. We can find that the trend is the same as what we found before, just like this one. This is the EC coefficient as a function of the electric field. We use the Landau-based models also can copy this trend. So, next step, we also calculate the microscopic insight. This is the percentage of dipole lying along 111 direction, but we choose have positive Z component. So there should be have 4 direction. Here, sorry, I forget to remember this. For BZT, our applied electric field is along 0001 direction. So there is 4 direction. From the picture, we can see that the ratio of the percentage of dipoles and the function of electric field have a peak around 1.2 by 10.8. This electric field is the peak is associated with the EC coefficient as a function of electric field. In other words, we calculate the percentage of dipole lying along different directions, can understand the microscopic insights, just the rearrangement of the dipole to understand the EC response. The next is EC effect in PMN, in prototypical PMN relaxer. Here, we apply electric field is along 111 direction. Why we choose along 111 direction? Because experiment already is predict when you apply 111 direction along in PMN, there will occur first order transition. This is our Hamiltonian predict the polarization as a function of electric field. We found that below a specific temperature, there should occur first order transition, and 320 Kelvin and 350 Kelvin is first order transition, but equal or above the 360 Kelvin, it from first order transition become to second order transition. So this temperature should be the critical point in PMN. Next, we plot the phase diagram for different temperature. Here is the first is the first order transition lines. We also plot the percolating lines, rhythm line, and alpha max line, I will see later. Then we calculate the calculate the electrocaloric effect coefficient for different temperature. Why we choose the two temperature? Because this temperature is near the critical point. We also show that the critical point is about 360 Kelvin. So we choose this temperature is near the critical point. This temperature is far away from the critical point. From the picture, we can see that we find a giant EC response at intermediate electric field. This magnitude electric coefficient is agree with the experiment. In other words, we also find a giant electrocaloric response or near the critical point, just near the first order transition. But at higher temperature, we also find this value is also bigger. In other words, in PMN, near the critical point, we'll find a giant electric response, but higher temperature is also have a bigger electrocaloric response. This picture, we just use the MC simulation based on the cumulative method. Why we just use this one? Because in PMN, about the ergodic, we just can use the indirect method. But below the below the critical point, we can't use this formula because this is can't use to calculate the electrocaloric effect. Then we also use the lambda-based model to fitting our EC coefficient and function as a function of electric field. We can see that this model can get very good fitting to our data. Next is we calculate the alpha max as a function of temperature. We find near the critical point, we find giant electrocaloric coefficient. This is agree well with the experiment found. Next is percolating in PMN. I first introduce the two parameters. The first is the strength of the percolating cluster. The second is average cluster. The N infinite is represent the numbers of the lead sites belong to the percolating cluster. This is the lead site in all the supercell. The second is about the N. The N represents the number of the cluster size belong to the polar region. So use this two parameter, we calculate the percolating in PMN. We found and we also choose the two temperature because before we can calculate the EC response for the two. Found that and this electric field change, the system begins to percolating. This field range is associated with the alpha max. Is associated with the alpha max we found. But at 500, because the cluster size is smaller than 308 Kelvin, so we need more bigger electric field to percolating this system. This is the 3D snapshot of the dipole configuration and 300 Kelvin. And when there is no electric field, we can see I need to introduce is the green line is along 111 direction because our electric field is along 111 direction. When there is no field, we can see the system is no percolating. But when we choose the percolating electric field, we found the percolating through all the supercell. Lecture is about the local feature impairment. We also calculate the percentage of dipoles lying near the 3 rhombohedral direction. Why we choose the 3 direction? In BDT, we choose 4 because in BDT we apply the electric field is along 001 direction. So BDT is 4 direction. But here we apply electric field is along 111 direction. So here we just have 3 directions. We find this percentage of dipoles have a peak and intermittent electric field. This field range is associated with before EC response. We also check at more bigger temperature. You can see this is a EC coefficient and function of the electric field. We find peak around 1,000 kV per cm. We also found this peak is associated with the local features, just about the percentage of dipole. The last is the conclusions. EC effect in BDT and PMN. First, we get for any temperature, alpha exhibit no monokinetic behaviors with DC electric field. The second is the maximum alpha for given temperature is related to some specific local feature. The local feature is we choose dipoles along different rhombohedral direction. The third is we use a simple lambda-like model to reproduce the EC response. The fourth is a giant EC response occur near the critical point in PMN. This is also agree with experiment results. The last is giant EC response induced by field-induced percolating of polar region. Thank you for your attention.
Okay, thank you. So are there any quick questions in the audience? Yeah, if not, our next speaker could come up. Does anyone have any questions? Yeah, please.
I'm a little bit confused by your second case. You apply electric field along 111 direction, right? But
yeah.
You also calculate the percentage, right?
Yeah.
But why it's peak at an intermediate electric field?
What?
Why the peak is at the intermediate electric field?
Because from the lambda-based models, it should have no monotonic and the function of the electric field.
I'm just saying you apply electric field along 111, isn't higher electric field just going to align more dipoles along that particular direction, and therefore you have a higher percentage of dipoles along that particular direction?
Yeah, but you mean this one?
The next one, right here.
This one?
Yeah.
Yeah.
No, the figure on the left. The R is the percentage of dipoles lying along the 111 direction, right?
No, just the percentage of the line near. This is not 111 direction. We just accept the 111 direction. Just choose 3, 1, negative 1, 1, 1, negative 1, and negative 1, 1.
Yeah, why the curve doesn't keep going up? Yeah.
Because initially the dipole is disordered when we not along 111 direction. When we apply the electric field along 111 direction, maybe some dipole want to must change his direction to 111 direction. So we just calculate the how many dipole along different 111 direction want to change.
Okay, so basically you're calculating the percentage of dipole that are not aligned with electric field. Is that okay?
Yeah.
Okay.
This is not along the electric field. Electric field is along 111 direction.
Okay, I think with that, and in the interest of time, let's thank our speaker once again. A little technical difficulties.
All good? Okay. Finally. Okay.
Okay, sorry. The connection's a little. This is our last speaker for the afternoon session is. Don't touch this. Yeah, you can't touch the HDMI connection. It's a bad technology. So if someone's trying to improve solid state.
Okay, back off.
Okay, I'll just please begin.
Sure, yeah. Good afternoon, everyone. My name is Jun Oh-Yan. I'm currently a visiting professor at Honda College of the City University of New York. And first of all, I'd like to thank the chairman and the organizer for giving me this opportunity to talk about my collaborative work with my host, Professor Ren, at the physics department of Honda College. So, title of the talk is demonstration of ultra-high recyclable energy densities in domain-engineered ferroelectric films. So, first of all, I'm a mature scientist, so I would like to give a general background about how to design ferroelectric thin films, just to give you a general background. Then talk about high energy density dielectric capacitors, why they're important, and give you a specific way of designing them by utilizing the polydomain structures that are usually formed in epitaxial ferroelectric films. Then I'll give you my example. My model system is barium zirconium titanate. It's 20% doped in barium titanate matrix, so 20% zirconium, 80% titanium. And how I achieved a mix of competing polydomain structures by phase engineering and strength tuning. So that's a design point. Then I'll give you the experiment data, structural analysis for XRD, TEM, second harmonic generation, and also electric characterization results, PV, CV, and CF results. Then from the PV, actually, you can get the energy storage density and also the efficiency. As conclusion, I'll compare the performance of my BZT thin film capacitors with some of the top performers in the field. So here's the film that you grow on a substrate. So obviously, you need a substrate to support it and also for integration purpose. And you will have an interface between the film and substrate. And the film is strained by the substrate. You're going to have strain effect. And also the film is usually have some defects. For example, for perovskites, oxygen vacancy is probably the most important one. So knowing this general background, then for perovskite ferroelectrics, you can design from 3 different major approaches. First, about interface. Interface, of course, is a gate that controls the charge transport. And sometimes when you have multilayer thin films, you're going to utilize the interlayer coupling to achieve some of the functionalities that you won't get in single layers in films. And the strain is the most important effect that substrate impose on the film. You can tune the property of the current phase, or you can achieve some new phases, so-called strain-stabilized phases. In thin films, there's a lot of examples in bismuth ferrite oxide films. And also, you can tune the polydomain structures. And also in non-epitaxial films, for example, the polycrystalline thin films, you can tune the grain structures by utilizing the strain. And the third aspect is the chemical control, the stoichiochemical control of the thin film. Basically, if you grow an epitaxial film, but you don't do good chemistry, so you will get leaky dielectrics. So epitaxial doesn't guarantee you a good film. So, but I won't touch this point, but just give you a general background about design of a ferroelectric thin film. So here I'm going to mostly talk about the PV hysteresis. So here is a very classic PV hysteresis. For example, if you have a single domain tetragonal film, your polarization is aligned with the electric field, so there's not too much you can change. Your remnant polarization is about the same, so slightly slower than saturated polarization. So this is very good for memory, as we all know. But if you look at this area, the green area, which means you go up to PS, you can go back. The green area is the part of energy that you can recycle. The yellow area within the loop is all lost. So that's from the dielectric capacitor point of view. So if you want to change this hysteresis loop, let's say we still make the film homogeneous, a single phase, single domain film. You want to get some type of different PV loop. You can change the phase, right? You can change it from tetragonal to rhombohedral. So now you apply a 001 electric field. Eventually, your polarization can align more with the electric field, so you have a big difference between the remnant and the saturated polarization. That's the intrinsic way to do it. But there's another way, I think it's well known in the field, that you can utilize an interface layer, so-called space charge layer or dead layer, to tune your ferroelectric PV loop from a square-shaped loop to a more slim loop. That's well known in the field. So here, I would propose a way of introducing inhomogeneity in the thin film. So I'm not having a single-phase, single-domain film anymore. Instead, I can have relaxer, polar nano regions, or we can engineer the grain in polycrystalline film, or the domain structure in epitaxial film. You can see here's an example. If you have a single domain to start with, so you can, of course, you can change it substantially by applying a field. So this feature, the characteristic for this loop is very easy to saturate, but very difficult to discharge, right? It's difficult to make the remnant polarization to disappear. But if you have a polydomain structure, which has a head-to-tail configuration of domains, and this polarization is canted to the applied field. So in the remnant state, you will have apparent zero polarization to begin with. And when you charge this film, of course, one of the domain will be favored, one set of the domain will be favored, but this is at the cost of removing the domain interface. So it's very difficult to be saturated. At the same time, if you discharge, because the head-to-tail remnant configuration is stable, you can get close to zero remnant polarization. So this kind of structure is very good from a dielectric capacitor point of view. So let's go back a little bit about the dielectric. We know the linear dielectric, for example, alumina polymer, linear polymer, the energy density stored in a linear dielectric capacitor is just the area between the dielectric displacement and electric field. It's linear, right? You can use a very simple equation to calculate that. But for nonlinear dielectric, for example, ferroelectric or antiferroelectric, they're different, right? So the key, like I just mentioned, to improve the recyclable energy, that's the area outside of the loop. You're gonna have a very small remnant polarization and a very large saturated polarization to achieve that. At the same time, another key parameter you need to consider in the design is to improve the applicable electric field as large as possible, because this energy that you can store is only in proportion with the dielectric constant, but it's in proportion with the square of the largest field that you can apply to this dielectric capacitor. So we can have different ways to design it, like I just mentioned. We need to switch from a square-shaped PV loop into a slim, tilted PPE loop. We can design it by grain structure, nano-grain structure. We can design it by interface. By utilizing this interface, we can use relaxers or we can utilize the domain structure. And this is what I'm going to talk today. So technical background, this is a new paper just published last year about all different kind of dielectric capacitors. So the y-axis is the energy density, and the x-axis is all different technologies. You can see some familiar things there. You can have the multilayer ceramic capacitor, nanodielectrics, and this is developed by Murata, that's a Japanese company. And you can have also have anti-ferroelectric composites. So the highest that reported so far is somewhere near the 30 joule per cubic centimeter. But in my work, I'm going to show you that by properly engineer the domain structure in the barium titanium oxide-based Fe film, you can achieve energy density several times higher than the current record. So for application of this dielectric capacitor, of course, we know its major application is power electronics and for power conditioning. Therefore, because they're so fast, if you can improve the energy density, you can use it in some future technology, for example, hybrid or electric cars as an inverter, capacitor, or you can invent some hybrid batteries or high-speed energy storage units. So a little bit background about the elastic domains. Dr. Roybert gave a very nice background, so I'm not going to spend too much time. But here, we know that the elastic energy, as you grow a strand film on substrate, it increases with film thickness. So very thin film, of course, you don't like to have interfaces. It's a strand uniformly across in the bark. But when you grow film above some critical value, you're going to form polydomain as a way to relax the epitaxial stress energy. As you grow film even thicker, you're going to form a higher order or so-called hierarchical polydomains. It's kind of like a fishbone domains. I believe a lot of earlier presenters already showed some nice pictures of this second order or higher order polydomain structure. So you're basically trading the residue elastic strain energy. You're reducing the elastic strain energy at the cost of extra energy associated with creating extra interfaces. So for these films, the second order or higher order films, these polydomain films seems like they're not very useful for memory application because the domains that usually aligned with polarization head to tail. The remnant polarization is likely to be close to 0, and the overall apparent polarization actually is unwilling to align with the electric field because of the interaction between the domains. So this is good for one type of technology, but maybe not. So for dielectric capacitors, this could be an ideal candidate. So again, I just zoom in the picture I showed you earlier a little bit. If you begin with a polydomain with a head-to-tail configuration, so the apparent remnant polarization is close to 0, and when you apply a field, so you're going to change the polydomain structure into close to a single domain structure. But if you discharge it, because these domains are their equivalent and remnant, they would like to stay in this head-to-tail configuration, you can discharge most of the energy that you initially put in the ferroelectric capacitor. So that's the idea from domain engineering point of view. We would like to have this kind of polydomain structure to begin with. So if we can have, instead of this so-called first order, we can create even a step further, we can create a second order. So this is the domain that I show you here. But if you can have even finer domain structures in these first order domains, that could be even better. Because as you go smaller, this domain structure, so-called nano domain structure, can become very adaptive to the change of field. So in order to create such a polydomain structure, I start from scratch with the barium titanate. We know barium titanate in the undoped state is a very stable tetragonal. I try to do some polydomain film out of only single phase, only the barium titanate, but I always get the polydomain of tetragonal. It proved to be not too much use for the dielectric capacitor applications because they're very difficult to switch, 90-degree domains, as you all well know. So I try to make it a rhombohedral, like I said, allow the polarization have a certain degree with the applied field. So in this case, I dope it with a little bit larger iron zirconium. It's larger than titanium. So you drag the stable phase from tetragonal to orthorhombic until you go to the rhombohedral. until you hit 25 or higher, you get a relaxer. I don't want to go to that side. So I pick something at 20%. We know it's rhombohedral in the bark. But at the same time, if you grow this composition, a film of this composition on a substrate, the substrate, the symmetrical implant compressive stress will stabilize the tetragonal phase, as we all know in the classic case of bismuth ferrite. So if we control a bulk stable phase rhombohedral, but we grow it on a cubic substrate, so I can stabilize my tetragonal phase. In this case, I have possibilities of creating two types of polydomains. One is when the film is thin and the residual strain is very high, I can expect a tetragonal rhombohedral mixed phase, just like in the case of bismuth ferrite. But when the film is thick or the strain is relaxed, I can expect some sort of rhombohedral dominant kind of microstructure, and hopefully I can have some of the higher order polydomains. So that requires that I grow the film really thick, not a few hundred, but into the micrometer level. So that's what we did experimentally. Before I show you any experiment data, I just elaborate a little bit of my point here. So you can see here, this is free energy as a function of misfit strain, right? I use the reference state is rhombohedral. You can see when there's no strain, the minimum is here. And this green curve is tetragonal. Of course, it's higher. The ground state is higher. But when you put it on a substrate, there's some certain misfit range that the mixed phase is become more stable, right? I don't need to say more about it. People already know it in bismuth ferrite case. But you can see when the misfit strain is higher, it's close to the self-strain of the tetragonal phase. So the dominant polydomain structure will be a tetragonal rhombohedral mixed phase, just like in the case of bismuth ferrite. In this case, you have a finite remnant polarization, but you probably can harvest a little bit more of energy density because you apply the electric field, you're going to change one phase into the other. That costs you extra electric energy. But if you have a very thick film, you're going to have a dominant rhombohedral structure, hopefully, if we can have this hierarchical polydomain. So in this case, your apparent polarization close to zero, and this polydomain structure ideally can have close to 100% charge-discharge efficiency, like I just described in the beginning. So in this case, not only we need to grow film on different thickness, but we also tune the film misfit by growing them on different substrate. So this is one of the typical XRD results. I show you the XRD results of this BZT film grown epitaxially on strontium titanate. You can see very nicely all these Z0L peaks, and you can see actually there are two peaks on the BZT. So one is tetragonal, one is rhombohedral, and we did 5 scans of both peaks, just showing you nice 4 peaks, indicating the epitaxy quality of the film. And we did some very intensive TEM work. We checked all the 4 different thicknesses from 350, 700, 1.4 micrometer. The thickest is 1.8. Here I'm showing you just as an example. This film is about 700. This is 200. The scale bar is 200. So this is about 700 nanometer. You can see all these column-like structures. And then when you zoom in, you can see all this nicely oriented zigzag kind of domain structure with a 45 degree with respect to the growth direction. So by just looking at the crystallography, you can tell all these are the higher order domain structure of rhombohedral. And then we did some select area diffraction work. So near the interface, that's the C, the circle C, we found that, of course, we found the substrate, we found the bottom electrode, and we also found tetragonal and the rhombohedral spots. And the rhombohedral spots, actually, when you grow more into the film bark, which is D here, you can see the tetragonal peak, actually, the tetragonal spots disappeared, but you have some very fine structure in the rhombohedral diffraction spot. And eventually, we figured out this is because you have 2 sets of rhombohedral microdomains, which grow from the bottom interface up until the surface of the film. So with this information, we did some second harmonic generation study. By the way, we have very intensive second harmonic generation results presented in a poster, and feel free to take a look. And we also have some nice acoustic phonon results there. But here, the basically we took the depolarization second harmonic generation signal, and the intensity of this signal indicates the volume ratio of rhombohedral. The higher the intensity, the more rhombohedral phase you have. So we did, I show you one on the left is the SSG spectrum for the thinnest film, 350 nanometer. And this one is for the thickest one. You can see the intensity actually grow almost twice. So based on the TM, XRD, and the second harmonic results, I can show you the schematic of the structure. So when the film is thin, dominant structure is T and R. When the film grows thicker, you have dominant rhombohedral structure, and you have some spots. When there's a highly stressed region, you can have tetragonal phase there to relax the growth stress. So that's the structure that we envision from the experimental results. Here, just quickly show you the experimental results. So these loops are for the thin film. You can see very slim, but still you can see some loss there. And this film has an efficiency of 85 to 90. But when you grow really thick, you almost think you're looking at a linear dielectric. Actually, they're not. If I enlarge them, you can still see the ferroelectric loop. But they're very, very slim. So the energy density, of course, the highest is for the thinner film, which you can apply higher field. Is about 170 joule per cubic centimeter. And the thicker film actually have an efficiency close to 100. Actually, the best record we got is 96% of the film grown strontium titanate. And here I show you the low dielectric loss of this nano polydomain film. This is a film grown LAO. It's about 2 micrometer. We apply basically 400 volts on the film. You can see the loss stays low up to the megavolts per centimeter level. That's good quality film. And we also did temperature stability study. We cooled down the film down to minus 170 and heat it up to 200 degrees C. You can see the energy change within about 10%. Efficiency, eventually, there's no change. It's all about 90%. And here's the dielectric dispersion. And you can see, very surprisingly, very stable dielectric constant. And we propose a mechanism of adaptive nanodomain. So the nanodomain can really respond to the field change when comparing with the large-scale domains. And here is the cycling performance. We cycle the film up to 100 million times. You can see here is the change in polarization. So you can see the maximum polarization actually only changed by 20%. From after 100 million times, the maximum polarization becomes 80% of the initial one. But what changes most is the remnant. It becomes only 40% of the initial. So with this information, you can calculate the energy change, the energy density change, and the efficiency. Efficiency actually slightly increases, more close to 100% after 100 million times cycling. And the energy density actually decreased about 20%. I think that's a very good record when you think about chemical supercapacitors. Usually they cannot cycle this many times. So the hypothesis here is the strength stabilized T phase, when cycled 100 million times, they transform to the box stable phase, R phase. So we have some more results which support our hypothesis. And we have some nice work actually in progress, trying to explain the cycling performance, comparing the performance of some fresh and some fatigue capacitors. And here just put you in the perspective how this compares with some of the top performers. Dielectric polymer, they're good in dielectric strength, but they're low in dielectric constant. That's why they're in this corner. And some of the lead-based ceramic, the high dielectric constant, but they cannot induce high voltage. But this blue line is my BZT thin film capacitors. It's good both in dielectric constant and the dielectric strength. And if you put in this famous chart, you're always looking for electric device with both high energy density and high power density, and this is where this work is at. So with that, I'm going to conclude my talk here. Last year, I actually presented some work of utilizing interface coupling. I grow a bilayer BTO BFO film. I show that I can significantly improve the energy density of a BTO almost 60%. And this year I show you that I can engineer the polydomain structure in BTT films to achieve very slim hysteresis with very high energy density. And in the future, actually, I'm going to show you, hopefully, if I'm lucky enough, I present again next year of how to utilize nano-gray engineering to achieve the same kind of PV curves. With that, I thank you and I welcome your questions.
Okay. So James had to run and catch his plane, so I'm taking his place. I think at this point we only have time maybe for 2 quick questions. Okay.
Nice talk. Just whether, I'm not sure if I understood, why did you put 20% of zirconium? It's to approach rhombohedral and tetragonal energies together?
Let me just show you here. So, okay, sorry. You can see when you dope with zirconium, actually you change the ground state from tetragonal to rhombohedral, right? Then when you put on the substrate likes it to be tetragonal because of the symmetry of the in-plane compressive stress. That's how we stabilize the tetragonal phase in the film. But when you grow really thick, the stress more or less relax, you're going to have those hierarchical polydomain structure of the rhombohedral ground state phase.
Okay, so let's thank the speaker and all speakers.
Thank you.